Hi there. So a lot to cover in this section. In section 1.5, we'll be looking at linear equations, functions, zeros, and applications of linear functions. I'm sure that you already have some familiarity with solving linear equations, and hopefully you recall that when you're solving a linear equation, your goal is to solve for the variable, and the variable is just a letter. So let's get myself a pen. Our goal is to solve for the variable. And like I said, that variable is just the letter. In most cases it's an X, but a lot of times it can be Y, B, C, D, whatever letter is used. A lot of times what I will tell folks is your goal when you're solving equations are that you want letters on one side, numbers on the other. Letters on one side, numbers on the other. And then it should be noted that when you solve linear equations, it's possible to have one solution, no solution, or what's referred to as infinitely many solutions. Okay, so we'll look here in example 1. I think I'm going to run through example 1, 2, and 3 here for you. So looking here in example 1, there are lots of different ways to solve equations. I'm just going to always try to present you in most cases with just one way, but there are multiple ways. What I always like to do is to tackle my letters first. If I don't have any fractions to get rid of, or if I don't have any parentheses, then the first thing I like to do then is I'll combine like terms. I don't have any terms to combine, then I like to do my letters first. That way, whenever you get to your special cases, if you do the letters first, the special case will present itself much quicker and save yourself some steps. So what I then do is I look at my letters here between positive 2x and negative 8x. I ask myself which is the smallest. And hopefully you would agree that negative 8 is definitely smaller than positive 2. So I always take then the smallest variable over to the other side, because if you take the smallest one over, a lot of times you can avoid them working with negatives. So anytime you cross the equals mark, you do the opposite. So the opposite of negative 8x would be to add 8x. Make my pen a little smaller. Add 8x. That way, over here on the right-hand side, the 8x's cancel out, and I always try to keep myself lined up down the equals mark. 8x plus 2x is 10x, plus 10, just bringing everything else down, equals 40. Now from here, I've got this number over here all by itself. That's good, because you remember you want to get closer and closer to having letters on one side, numbers on the other. So since that 40 is over here all by itself, leave it. Take the 10 over to join it. Because you're going to cross the equals mark, do the opposite. So since it's plus 10, I'm going to subtract 10 from both sides. That way it cancels out over here. Leaves me with 10x on this side. 40 minus 10, of course, is 30. Then my last step, I want to get this letter all by itself. This is 10 times x. How do we undo multiplication? We just divide. You always divide by the number beside your letter. And so 10's beside my letter. I'm going to divide both sides by 10. That way over here, 10 divided by 10 cancels out and just leaves me with x. And then over here, 30 divided by 10 is 3. Final answer. Now, I'm going to show you this on the first problem. Anytime you solve an equation, you can always go back and check yourself. And the check is very straightforward. So you just take your original equation, so I have 2x plus 10 equals negative 8x plus 40. And everywhere I see an x, I plug in what my solution was. So here my solution is 3, so I'm going to plug in 3 for all my x's. And if I get the same number on both sides of the equals mark, then I've solved this equation correctly. So of course over here on the left-hand side, 2 times 3 is 6. 6 plus 10, 16. So let's make sure we can get 16 over here. Negative 8 times 3 would give me negative 24 plus 40. And then when we combine this, 40 minus 24, that's also going to give me a positive 16. Okay, so this x equals 3 is definitely my solution. This is the way to check yourself to make sure you get the same thing on both sides of the equals mark. Okay, all right, now let's go down over here to example 2. And then in the next two examples, you'll notice that they have fractions. I don't know about you, but I don't particularly care to work with fractions. I'm going to show you a way to get rid of your fractions. And all that it entails is just multiplying by your common denominator. So you look at all the denominators associated with the problem. And so in our case here, the two denominators are 5 and 10. And we ask ourselves, what's the number that 5 and 10 will both go into? And so they'll both go into 10. So I'm going to multiply this entire equation by 10, and that means that I multiply every single term. So I've got 4 terms here to multiply by 10. And then you might say, well, I'm still having to work with this fraction. Well, let me show you a way to so you don't even have to go to a calculator at this point. You always take the 10 that the common denominator that you're multiplying by, take that and divide it by the denominator, and then whatever answer you get, multiply up top. So this is what I mean. 10 divided by 5 is 2. 2 times 6 is 12. So it's 12y. Plus, next term, 10 times 3. It's just 30. Now I've got another fraction again, so I'm going to take 10 divided by the denominator here. So 10 divided by 10 is 1. 1 times 3 is 3. Minus. And then the last term, 10 times a negative y. Remember, there's an imaginary 1 here. So 10 times negative 1, negative 10y. And then if you're thinking at the moment, well, that was magic, let me come over here to the side and show you what I did. When I did that 10 times 6/5, think of that as 10 over 1. From here, you can just multiply straight across. 10 times 6 is 60. 1 times 5 is 5. And then 60 divided by 5, sure enough, is 12, which is exactly what we got. So it allows you, I just wanted to let you know that, that's why I can do what I did. Whatever common denominator you get, I'll say it one more time, whatever common denominator you have, take that number, if you have a fraction, divide it by the bottom number, and then take that answer and multiply up top. So I'll go through it one more time. 10 divided by 5 is 2. 2 times 6 is 12. Plus, next term, just multiply straight across. 10 times 3, 30. Got a fraction again. 10 divided by 10 is 1. 1 times 3 is 3. And then 10 times negative 1 over there would give me negative 10y. All right, so now I'm looking at, okay, I'm going to get my letters on one side, numbers on the other. Look at my letters first. Between 12 and negative 10, that negative 10 is the smallest. I'm going to take it to the other side by doing the opposite. So I'll add 10y. Cancels out over here. 22y plus 30 equals 3. Subtract 30 from both sides, right, because I want to get those numbers together. 22y equals negative 27. I'm going to come over here since I'm running out of room. Just rewrite that. 22y equals negative 27. And then my last step to get this y all by itself, this is 22 times y. Always divide by the number beside your letter. So divide both sides by 22. Cancels out. 27 and 22 don't have anything in common, but if you kind of question for yourself, I don't know if that can be reduced or not. If you put it in your calculator, negative 27 divided by 22, and then hit enter, it's going to give you a decimal. And then if you go to your math, enter in your calculator, then if it can reduce, it will. If it can't, then it's just going to spit this number right back out at you. Okay, so that just lets you know that it couldn't be reduced. But if it could be reduced, of course, it will go ahead and do that step for you. I highly recommend it, if you're unsure of whether something will be reduced or not. So it's a quick, easy plug into the calculator to see. All right, let's move on down to example 3. In an example 3, I've got fractions again. And, if you want to stop the video and try it for yourself first, then by all means do so. So just looking here at my fractions, looking at my denominators here between 4, 3, and 2, I ask myself, what's a number that 4, 3, and 2 will all go into? And hopefully you would agree that 12. 4 will go into 12, 3 will go into 12, 2 will go into 12. It has to be a number that all 3 of them will go into evenly. So now, anytime I do my fractions, so I'm going to 12 divided by the bottom. So 12 divided by 4 is 3. 3 times 3, 9x, minus 12 times 3, 36. 12 times x, 12x, equals, okay, I'm hitting another fraction. 12 divided by 3 is 4. 4 times 2, 8x, minus 12 divided by 2 is 6. 6 times 5, 30. Okay, so now from here, if you'll notice on the left-hand side, you have like terms. I would combine those before I go any further. So 9x plus 12x would give me 21x. So I have 21x minus 36 equals 8x minus 30. So then from here, I'll do my letters next. Between 8 and 21, which is smaller? Hopefully you agree. 8 is smaller. It's a positive 8x. So to take it to the other side, I subtract. 21 take away 8. That's going to give me 13x minus 36 equals a negative 30. And then negative 30 sitting over there all by itself. So I'm going to add a 36 to both sides. 13x equals positive 6. Divide by 13. So x equals 6/13. All right. In example 4, I'll just do the first step with you just to make sure that you're tracking. And if you feel good about it, then just go ahead and pause the video and you can check yourself by the solution key. Because I'm just going to do the first step. Here, this one's a little different only in the fact that it has parentheses in it. So I'm going to first distribute through. So I'm going to say 3 times 2x, well, that would give me 6x. 3 times negative 5 would be minus 15 and plus 4. Then take my 2 and distribute it. 8x plus 2 times 3 will give me 6. Okay. Then from there, combine like terms. And then take your letters over. And again, I always do my letters next. I take over the smallest. Okay. All right. We'll move on down to your special cases. Your special cases occur when your variables cancel out your letters. So that's the reason why I've been advocating for you to, whenever you're solving your equations, do your letters first, because if you do your letters first, then you're going to know very much earlier on whether they're cancel out or not, so that you'll be able to identify the special cases, like I said, sooner. Save yourself some work. So when your variables cancel out, so when your letters cancel out and both sides are equal, the solution is all real numbers or infinitely many solutions. When your variables cancel out and both sides are not equal, the result is no solution. Okay. So let's kind of tackle a couple of these down here. So looking at example 5, the first thing I see in the right over here is that I have a negative 2 in front of a parenthesis, so that negative 2 needs to be distributed first. So I'm just going to bring down the left-hand side, negative 6x plus 5, and start distributing. So negative 2 times 4, negative 8x. Negative 2, this minus is the same thing as a negative. Let your multiplication here determine your signs. So negative 2 times negative 8 gives me a positive 16. You want to get away from using double signs, okay? So like I said, let your multiplication here determine your signs. So negative 2 times positive 4 was a negative 8x. Negative 2 times negative 8 was a positive 16. So I put that at plus 16. And then I bring down my plus 2x. Over here on the right-hand side, I've got like terms, right? The 8x and the 2x, let's combine them. I'm not going to do the opposite. They're on the same side, so you just combine them. Negative 8 plus 2 will put you at negative 6x plus 16. And then over here, I have negative 6x plus 5. Now, from here, it doesn't matter which 6x you take over. You've got to do the opposite because you're crossing the equals mark. That's when you do the opposite, is when you cross the equals mark. So these 6x's cancel out. The 6x's cancel out. So at this point, okay, you're saying, all right, I've got a special case. The letters have canceled out on both sides. Now you look to see what you have left over. I'm left with 5 equals 16. Well, that is definitely not a true statement. 5 definitely does not equal 16. I need you to then tell me, okay, well, this represents the case of no solution. Okay. Let's move on over here to the next one. In example 6. In example 6, I've got some distributing over here on the right-hand side. And over here on the left-hand side, I've also got like terms. So I think what I'll do is I'll distribute first. I'll just burn an extra step here. Okay, so I think I'm just going to... It would be legal, though, if you want to go ahead and combine like terms on the left-hand side, but I think I'll just copy it down and I'll do all my combining all at one time. Distribute, I have 2x, 2 times positive 4 plus 8. Then I have plus 3x minus 3. Now, if I combine like terms on the left-hand side, 7x minus 2x, 5x plus 5. On the right-hand side, 2x plus 3x, 5x, 8 minus 3, positive 5. You might already notice here, well, they're already identical. And if we just take it one step further and say, okay, well, I want to get my letters all on one side. Doesn't matter which 5x I take over, right? What happens to them? They cancel out on both sides. But this time, look and see what you have left over. You have 5 equals 5. That's a true statement. And so what that means is that you could put any number you wanted to, a whole number, decimal, fraction in for this x, and you're going to get the same value on the left-hand side as the right-hand side. So you can write your solution as all real numbers. That's just the abbreviation for all real numbers. I can't remember if I've addressed that in the video or not. I think I did. That's the abbreviation here for all real numbers. Or you could say infinitely many solutions. Okay. And then lastly down here in example 7, I want to work through this one with you just because, but I think it might be good for you to pause the video first and try it for yourself. But anyway, I'm going to nevertheless work through it just because it's a little different. I want to make sure that I clear up any kind of misconception. Okay. So if I'm looking at this problem, I would then take my 5 here and distribute it through. So I have 9x plus 10. 5 times 4, 20x. 5 times -1, so minus 5 plus 15. 9x plus 10 over here. On the right-hand side, I'm combining like terms, so I have 20x plus 10. All right. Now, from here, if I do my letters, looking at my 9x and my 20x, again, there's multiple ways to solve it. You might choose to take the 20x over. I'm just looking at it here and saying, okay, well, between 9 and 20, 9's smaller. I'm going to take it to the other side. So subtract 9x. Some people like to always bring their numbers or bring their values over to the left. I just do the smalls so I can avoid my negatives. That way 9x cancels out and I'm left with 10 equals 20 take away 9 is 11x plus 10. Now from here, I've got this 10 sitting over here all by itself. Let's take the other 10 over to join it. 10 minus 10 is 0 equals 11x. And a lot of times some people say, well, after I've shown them what a special case looks like, they say, oh, something canceled out, so this has got to be another special case. Remember, your special cases only occur if your letters cancel out. Your letters didn't cancel out here. You still need to solve for this x. This is 11 times x. To get rid of that 11, to undo that multiplication, divide by the number beside your letter. But 0 divided by some number is still 0. So there's only one solution here, and it's x equals 0. Okay, so remember just because your numbers cancel out, 0 is still a number, so that's okay. But when your letters cancel out, that's when you reach a special case. Okay, so I just wanted to make sure that sometimes once I show folks the special cases, they just start to say, well, everything's a special case. But remember, there's more to it. You can have one solution, no solution, or infinitely many solutions. And these special cases only occur when your letters cancel out. Okay? All right, I'm going to flip it on over, top of the next page. Just an extension from linear functions refers to the zeros. And zeros will be something that we look at a little bit further in section 2.1, and I'll further show you in that section how to find zeros on your calculator. The zero of a function is defined as this. So a value c is a zero of a function f if f of c equals 0. So meaning if you can plug that value into the function and you get 0, then that value c there is referred to as what's called a 0. And another correlation here is that, well, if c is a 0, then c comma 0 is an x-intercept. So in other words, that 0 and the 0 is essentially the same as an x-intercept. Okay, they're very closely aligned with one another. It's just a terminology difference. And in other words, to find your zeros, you're setting f of x equal to 0. And if you think about it, f of x is the same as y. Remember back in a previous video when you were finding your x-intercepts, you let y equal 0 and you solve for x. So that's just trying to get you that correlation here. I'm trying to find my zeros, so I'm letting y equal 0 and solving for x. So here in example 8, in example 9, 8 and 9, it says find the zeros of this function. So I'll do example 8 with you and let you try example 9. I've shown my work on the solution key for you. So I have here, if I want to solve for my 0, then I'm going to take my function and set it equal to 0. So 2/5 x minus 10 equals 0. If I want to solve for x, there's multiple ways to solve this equation. I think what I'll do is, because it has a fraction, I'm going to get rid of the fraction for you, just so you get that practice one more time. So looking at it, and I've got this fraction. The only denominator I have here is 5, so that can be my common denominator. Just multiply by 5. Remember, for your common denominator, you only have to worry about denominators. You don't have to worry about any of the other whole numbers. So now at this stage, 5 divided by 5 is 1. 1 times 2, 2x. 5 times 10, 50. 5 times 0, 0. And now this is hopefully you would think of this as being a little bit more straightforward. So I can add 50 to both sides. 2x equals 50. And then divide by 2. And so x equals 25. And so what this means is that 25 is a 0. 25, kind of looks a little weird there, doesn't it? Let's try that again. 25 is a 0. And if you were to look at a point on the graph, the point 25, 0 is an x-intercept on the graph of this function, is an x-intercept. Okay, so, but essentially it said find the zeros. So your final answer here then is 25. 25 is your 0. I just want to hit home here that, yeah, we found that 0. What does it mean? It's an x-intercept. It's a point where your graph is crossing the x-axis. I think it might be worthwhile also here to show you a different way to solve this equation, just in case you might have done it, and I don't want you to ever think that your way is wrong. Here's another way. It's legal. We can add 10 to both sides, right? Because your goal is to get letters on one side, numbers on the other. So if we do that, we have 2/5 x equals 10. Now, from here, hopefully you might recall this from a previous course. In order to get rid of this letter, you would divide by the number beside your letter. So you would divide by 2/5. In cases like this, I always tell folks, multiply by your reciprocal. Because when you multiply by the reciprocal, whatever you do to one side, do to the other. But notice what happens when things are diagonal, they cancel out. So the 5s would cancel out, and the 2s would cancel out, and that just leaves me with x. And then look what happens over here. 10 times 5 is 50. 1 times 2 is 2, and 50 divided by 2 is 25. So you get the same answer either way you do it. I just wanted to address an alternative way to solve this equation. All right. Again, pause the video, try example 9, check it by the solution key. All right, let's look at example 10 then. In example 10, it says, given the graph below, they want us to identify the x-intercept and the 0. So x-intercept, remember, that's very intuitive. It's where you cross the x-axis. So hopefully you agree. This graph is crossing the x-axis down here at 8. X-intercepts are always written as ordered pairs, so that's why I'm writing that there as 8, 0. It's asking now for the 0. So for the 0 part, you would just write 8. Okay, that's essentially the only difference. The 0 is where the function equals 0, and so this is where that function equals 0. And the x-intercept is where you cross the x-axis. So the only difference is how they are noted. An x-intercept is a point, a 0 is just a number. Okay. All right, let's scoot on down here, and then the last we'll wrap up here at the end of the section here with solving linear application problems. So I'm going to do example 11 with you. Example 12 is very similar to this one. I'll let you pause the video and try example 12 on your own. This is what I call as a comparison type problem. You'll see why here in just a moment. So you've got 3 friends here, Jen, Kate, and Mark. Each received a scholarship to go to college. Jen was awarded $1,600 more than 3/4 Kate's amount. So Jen at the moment Jen's scholarship amount is being compared to Kate. Mark was awarded $100 less than half of Kate's amount. So Mark's scholarship award is also being compared to Kate. Together, the 3 friends were awarded $4,200 in scholarship money. How much was each person's scholarship worth? Okay. So in order to set these up, I'm just going to abbreviate their names. So Jen, Kate, and Mark. And set it up like this. And I'm going to go back and do some translating. But here's how you get started on these. Whomever everyone is being compared to is your x. So that's why I made a point to say here in that second sentence, Jen's scholarship amount is being compared to Kate. Mark's scholarship amount is being compared to Kate. So whomever you're being compared to, both of those, Jen and Mark, are both being compared to Kate. So Kate is X. Okay, so Kate's the X amount. We don't know how much hers is. We don't know how much at the moment how much any of the three are, but we certainly don't have any other information about Kate. Now, if we go back to that second sentence, it says Jen was awarded, now we want to translate. Jen was awarded $1,600 more than 3/4 Kate's amount. So hopefully you would agree with that. $1,600 more than, that's going to entail that we're adding 1,600. 3/4 Kate's amount. So Kate's amount is X. I want to write 3/4 of that. That just means 3/4 times X. $1,600 more than, so adding 1,600, 3/4 Kate's amount. If you were thinking 1,600 plus 3/4 X, same thing, okay? That's perfectly legal. Let's go to our next sentence. Mark was awarded $100 less than half of Kate's amount. So $100 less than, so since it's saying it's less than, that $100, the subtracting of 100 has to come at the end. Half of Kate's amount, so 1/2 X this time. $100 less than half of Kate's amount, because remember, Kate's amount is X. You could not write this one any other way. You could not write that as 100 minus 1/2 X, because it's the way it's worded here is $100 less than half of Kate's amount. So half of Kate's amount is 1/2 X, $100 less than that. So it has to come that way, in that order. And we do know that Jen plus Kate plus Mark, so Jen's scholarship plus Kate's scholarship plus Mark's adds up to 4,200. So now, in place of Jen, Kate, and Mark, I can use these expressions. So Jen is 3/4 X plus 1,600. Kate's amount is X. Mark's amount, 1/2 X minus 100 equals 4,200. The nice thing about that now is that you'll notice everything's all in terms of the same letter. So I'm going to be able to solve this like a linear equation, just like we were doing on the front page. If you want to, now might be a good time for you to pause the video. I'm going to go ahead and work through this entire problem. But if you want to, this might be a good opportunity for you to, one more time, practice getting rid of these fractions, because that's exactly what I'm going to do next. So I'm going to multiply by my common denominator. So just looking at my two fractions between 2 and 4, I ask myself what's a number that they'd both go into. They both go into 4, so I can multiply by 4. If you were thinking 8 or 16, you can use those numbers too, but the smaller you go that they'll both go into is less reducing later, okay? So multiply by 4. 4 divided by 4 is 1. 1 times 3, 3x. 4 times 1,600, 6,400. 4 times x. You can think of this one as half of 4, so half of 4 is 2, but I'll do it the other way as well. 4 divided by 2 is 2. 2 times 1, 2x. 4 times 100. 4 times 4,200, and that would put you at 16,800. Okay. Now from here, combine like terms. Before you start moving stuff from one side of the equals mark to the other, combine like terms. I do my letters first. 3x plus 4x is 7x, plus 2 more, that'd be 9x. 6,400 minus 400, that would give me plus 6,000, equals 16,800. Okay, now my same goal, letters on one side, numbers on the other, so since the 16,800 is over here already by itself, I'm going to take the 6,000 over to join it, do the opposite. So subtract 6,000. So it cancels out. 9x equals 10,800. Divide both sides by 9. X equals 1,200. Can't stop there because it wanted to know how much was each person's scholarship worth. So at this point, that 1,200 represents who? And hopefully you would agree, well, since 1,200 is X, Kate's X, we now know that Kate was awarded a $1,200 scholarship. That's her amount. To figure out Jen's, in place of X, I've got to put in 1,200, so I've got 3/4 times 1,200 plus 1,600. So you could do this in your calculator, or you can think about it by hand as well. But 3/4 times 1200. See, I'm gonna do it since I don't have my calculator right here. So 1200 divided by 4 would give me 300. 300 times 3 would be 900 plus 1600. And then that would give you 2500. So Jen's amount was 2500. And then Mark would be half of that X value, so half of 1200 minus 100. Half of 1200, of course, is 600 minus 100. So Mark was awarded $500 in scholarship money. And then you could go back and do a nice loose check for yourself and make sure that 2500, 1200, and 500 all add up to that 4200 that they were awarded totally. Okay? Let's flip it on over then to the last page. Again, I highly recommend you stop the video, try example 12, and check yourself by the solution key. I'm going to look at the rest of the problems on this page, though, because they're all just a little different. Actually, in example 13, I'm going to half work it with you, okay? I think, anyway. So it says here in example 13, it says the kids at a daycare planted a rectangular garden with a perimeter of 39 meters. So you can think of it. I hate when it does that. Get back. Sorry. Okay. All right. I was going to try to draw you a picture. So a rectangular garden. Perimeter, hopefully you recall perimeter. Perimeter is distance around. Okay, so they're telling us that the distance around, so it's kind of like you putting up a fence or something. They're building this garden. It says that the perimeter around is 39 meters. So if I were to add up all these lengths and widths, that would total up to 39 meters. Then they're giving us some information here. So I'm just going to write that. The P equals 39 meters. They're giving us some information here about the length and the width. They're saying that the length of the garden is twice the width. So here's my width. I'm going to let my width here be x because my length is being compared to my width, right? Whatever you compare to, that's your x. So the length of the garden is twice the width. So I'm going to let my width be x. The length is twice that, so 2x. Hopefully you remember the formula for perimeter. P equals perimeter of a rectangle, I should say, because that varies according to the figure. P equals 2 times your length plus 2 times your width. And now plug in everything that you know. So get a different color here. So in place of my perimeter, I know that's 39. In place of my length is 2x. In place of my width is x. So now from here, that would give me 4x plus 2x. The advantage, or the reasoning for this, setting it up like this, is that now I have it all in terms of one variable. So now I have 4x plus 2x. Of course, that's 6x equals 39. Get x all by itself. I'm going to divide by 6. And so x equals 6.5. So now that you found this x, go back and say, okay, well, does that x represent the length or the width? Since my width is my x, okay, well, now I know that the width here is 6.5 meters. My length then is going to be 2 times that 6.5, or 13 meters. So, picture-wise then up here, now we know, okay, well, these two sides are 13 meters, and these two sides are 6.5. And if you go around your figure now and add up all those sides, it should add up to the 39 meters. Okay. All right, let's scoot on down here and look at example 14. Example 14 is a little tougher because it's just not that it's too terribly, not that much tougher. It just has a different technique in it. I should say it that way. It has a different technique for solving. Okay. All right. So Ken has 2 student loans totaling $9,000. Loan A has a 5% simple interest rate. Loan B has a 6% simple interest rate. At the end of the first year, he owes $492 in interest. They want to know then what is the amount of each loan. So let's talk about setting this up. if I were setting this up, I need to sort of identify some variables here. And I'm going to let I'm going to set capital A here is going to be the amount for loan A. So this is going to be loan A amount. Because it doesn't tell us. We know that the two loans together add up to $9,000, but we don't know how much loan A was and how much loan B was. So I'm trying to make it intuitive here that capital A represents the amount of loan A and capital B will be the amount of loan B. Now we can go ahead then and write one sentence or one equation here for us that A plus B, the amount of loan A plus the amount of loan B, adds up to 9,000. Now the other piece of information here is associated with interest, $492 in interest. So I've got to think about another formula. I've got to bring in another formula associated with interest, and hopefully you may recall this formula associated with interest, I equals PRT. That's actually the simple interest formula, and I utilized that one because both of these interest rates, you'll notice, were identified as being simple interest rate. So if I want to figure out then the interest that I'm going to accrue for loan A and the interest I'm going to accrue for loan B, let's think about it this way, that loan A's interest, P is the principal, how much you put in. We don't know. We put in A amount for loan A. The interest rate for loan A, though, is 5%. It's got to go in as a decimal, so 0.05. T stands for time. And we know that our interest amount that they've given us here is associated with the first year, so it's associated with 1 year. So if you multiply that out, then 0.05 times 1, of course, is 0.05 times A. So that tells us, okay, well, the interest associated with loan A would be 0.05A. Likewise, for loan B, the amount you put in would be B amount. We don't know how much that is. The interest amount, though, for loan B is 0.06. And again, it's for 1 year. So then that, if you multiply it out, would be 0.06B. Okay. So now I can write an equation based on these interest charges and the total interest. So I can say, well, the interest charged for loan A, 0.05A, plus the amount charged for loan B, 0.06B, equals a total of $492. Now, if you've ever solved systems of equations, you could actually use that to solve this particular equation. However, we haven't gotten to that. We will in a couple of sections moving forward, so I'm going to use a different technique here to solve. What I'm going to do, the reason why I can't just solve it, the linear equation at the moment, is because at this point, I've got two letters. And everything that we've looked at so far has always been in terms of one letter. So in order to be able to solve this, I need it in terms of one letter. So a technique to do that would be to take the top equation. You could take either equation, but here, taking that top equation and solving it for one of your letters is the easiest way to go. Always try to solve for a variable that has a 1 in front of it. I could solve for A or B. I'm just going to solve for A. So I'm just going to take that equation there, A plus B equals 9,000. You can solve for either letter you want, but if I solve for A, that means I want to take B to the other side. So I just subtract B from both sides. Subtract B. So A equals 9,000 minus B. What that allows me to do is to come to the second equation here and substitute it in. Everywhere I see an A, I can plug in this expression. So notice what happens now. 0.05 in place of A, I'm going to put in 9,000 minus B plus 0.06B equals 0.49. No, that's not a point. That's just 492. Sorry. Equals 492. Okay. Already at this point, I'm in terms now of just one letter B, and that's going to allow me to solve this as a linear equation as I have been. So now I'm going to take this 0.05 and distribute it through. So 0.05 times 9,000, that's going to give me 450 minus 0.05B plus 0.06B equals 492. Combine like terms over here, so negative 0.05 plus 0.06, that's going to leave me with 450 plus 0.01B equals 492. I want to get letters on one side, numbers on the other. 492 is over here all by itself, so I'm going to subtract the 450. 0.01B equals 42. divide by 0.01, and then that tells me now that B equals 4,200. So that I now know, okay, well, the amount of loan B is 4,200. To figure out now the amount of loan A, it would be just going back and substituting into your equation. You can use any equation that you want to, but this one right here is the easiest one to plug into because it's already solved for A. And so A equals 9,000 minus your B, and we just found B to be 4,200. 9,000 minus 4,200 would be 4,800. And that's your answer. So a little bit more involved, but you know, you've got to see different techniques so you'll be able to tackle various problems, okay? All right, and then lastly, example 15 is very similar to that one, so if you wanted to stop the video and try it on your own, you can. I think I'm going to take the time, though, to show it to you, show you all the steps, okay? So looking at example 15, it says a plane leaves the airport and flies due east at a speed of 80 kilometers per hour. 2 hours later, a jet leaves the same airport flying due east at a speed of 900 kilometers per hour. And we want to know how far from the airport will the jet overtake the plane. Okay, we're going to need to utilize the formula here for distance. D equals RT. Because essentially, you've got these two planes and they're both leaving the same spot. One's just traveling faster than the other, right? One's traveling at 180 kilometers per hour, and then the other one is leaving the exact same spot, is just traveling a lot quicker, and it's just leaving a little later at 900 kilometers per hour, and it did it 2 hours later. Okay, all right, so let's look at our two modes of transportation here. We have a plane and a jet. Plane and our jet. In terms of our plane, its distance could be calculated, its rate, it's traveling at a speed of 180 kilometers per hour. Time, it's traveling at t hours. The jet is traveling at a speed of 900 kilometers per hour. And the only thing different here is that it had a 2-hour delay in time, so I'm going to put t minus 2, right? It's in relation to the plane, it left 2 hours later, okay? Now, we know eventually the plane and the jet are going to catch up with one another. We want to know, well, when does that happen? So I want to know, when do these distances equal each other? So I'm going to set the plane equal to the jet. And so I'm going to set 180t equal to 900 parentheses t minus 2. And just solve for t from here. So just distribute that 900 over here on the right-hand side. So 900t minus 1800. I'll have my 180t over here. Now, this is a good example to talk you through, because typically, like I said, I always do my letters next, and I still will do my letters next, but I've been saying, take your smallest over. Well, between 180 and 900, 180 is smaller. But if I take it over here, then I have my letters and my numbers over here on the same side. At the moment, this letter is already over here all by itself. You want to keep it there. Take the other letter over to join it, because that's your goal, is to get letters on one side, numbers on the other. So since that letter's over there all by itself, go ahead and take it over there. It'll cancel out over here. 180 minus 900 is going to give you a negative 720t. And then this is going to be a negative 1800. Now, last step, divide by negative 720. Cancels out, and so t equals, and a negative divided by negative is going to give you a positive. And for the most part, I should go ahead and mention, if you're working through these problems and it's a real life problem, most of the time you can't have negative answers. Every once in a while you can, so I'm not going to say never, but most of the time you can't. So if something's kind of coming out and you're getting a negative time or a negative dollar amount, then you've done something wrong, okay, in terms of whether it might be a setup or you misdistributed or you forgot to distribute something. So here, I think it just wanted to know the time. Oh, nope, actually it wanted to know how far from the airport is the jet. So this is giving us our time. If we want to know, okay, well, what was the distance? Then in order to figure out that distance, I'm going to have to come back up here and plug that in. 180 times 2.5. And so 180 times 2.5 will land you at 450 miles. So that plane would get to travel 450 miles before the jet was able to overtake it. And you could plug it into either one you wanted to. If you wanted to come down here and plug in 2.5 down here, 2.5 minus t, 2.5 minus 2, excuse me, is 0.5. Half of 900 is also 450. So you're going to get 450 miles either way you do it, okay? So in 2.5 hours, they would have traveled 450 miles and they would have overtaken one another, okay? All right, I know this was a long video, but there's a lot to cover here. Thanks a lot. Bye.